The purpose of this lab is to study the behavior of objects under the effects of gravitational forces. The force of gravity by one object onto another object is represented by the formula -g times the mass of the first object times the mass of the second object divided by the magnitude of the distance between the two objects squared, all times the direction between the two objects. I also explored the effects of the force of gravity by measuring an object's parallel and perpendicular force components. The formula for the perpendicular component is expressed through the equation mass times velocity squared divided by the radius. To study these behaviors, I used a few simulations of objects in space influencing each other with their gravitational forces. In the first simulation, I used the properties of gravity to measure the mass of a black hole that has a star orbiting around it. In the second simulation, I determined the initial velocity of a spaceship needed to get close to the black hole without colliding with its event horizon. In the first simulation, I used the properties of the gravitational force between a star and a black hole to determine the black hole's mass. For the initial conditions in the simulation, the star had a mass of 2 times 10 to the 30 kilograms, and the change in time for each time step would be the number of seconds in an Earth day. First, I calculated the value of the net force acting on the star by calculating its change in momentum over the change in time. Then, using the formula for gravitational force, I isolated the mass of the black hole on one side of the equation to find the mass of the black hole. Gravitational force is set to equal net force because gravitational force is the only force acting on the star in the simulation. Additionally, I calculated the perpendicular and parallel components of the gravitational force and represented them as arrows on the simulated model. By running the simulation, the net force increases as the displacement between the star and the black hole decreases. The star's momentum reflects the change in the net force. Due to the non-constant net force, the calculations for the black hole's mass change throughout the simulation. By collecting an average of the calculated mass values, I found that the mass of the black hole is approximately 1.61 times 10 to the 34 kilograms. In the second simulation, I used the properties of gravitational forces to determine the initial velocity required for a ship to escape a planet and pass by the black hole from part 1 without colliding with its event horizon. For the simulation's initial conditions, the mass of the black hole would be 1.61 times 10 to the 34 kilograms, the mass of the planet would be 9 times 10 to the 28 kilograms, and the mass of the ship would be 7 times 10 to the 10 kilograms. The planet would be 10 to the 10 meters from the black hole in the x direction. The ship would begin at the side of the planet facing the direction of the motion. To get the simulation to work properly, I needed to calculate the motion of each object based on the gravitational forces they exert on each other. First, I used the gravitational force formula to calculate the net force acting on both the planet and the ship. This required that I calculate the gravitational force of the black hole on each object, as well as the gravitational force of the planet and the ship on each other. Using the net forces for the planet and the ship, I used Newton's second law to calculate the velocity of each object for each time step. Then, I used the velocity calculated for the position update formula to allow the simulation to simulate the motion of each object. For the first time running the simulation, the ship had crashed into the planet. I needed to assign an initial velocity to the ship such that it would evade both the planet and the black hole, but also get very close to the black hole during its travel. I would also need to consider that the ship's velocity cannot exceed the velocity of the speed of light in a vacuum. After playing around with the values for a bit, I found that the x component for the initial velocity would be -1 times 10 to the 8 meters per second, and the y component would be 1.8 times 10 to the 6 meters per second. While this velocity makes the ship very fast, it does not exceed the speed of light. In my experiment, there are possible sources of error. For each simulation, there was no calculation conducted for the behavior of the black hole's motion. Despite how small the impact that the other object's gravitational forces would have on the black hole of its size, there would be some effect. How do the parallel and perpendicular components of net force differ from the parallel and perpendicular components of the rate of change in momentum? Net force and the rate of change in momentum are equal to each other. This fact allowed me to make the necessary calculations in part 1. Therefore, their parallel and perpendicular components are also equal to each other. This tells us the rate of change in behavior in an object's motion mimics the effects of the forces acting upon it. If instead of leaving the black hole's system, the ship went into orbit with the black hole, what would the initial velocity need to be? After testing different initial velocities, I found that an initial velocity that leaves a ship in an orbit around the black hole has an x component of -1.5 times 10 to the 6 meters per second, and a y component of 1.1 times 10 to the 7 meters per second. By comparing these values to the ones used in part 2, this velocity has a y component much greater in magnitude to the x component. In conclusion, this lab shows the relationships between different variables such as momentum and net force. It also shows how simulations can use different formulas to predict the motion of objects.